Good evening and welcome to Physics with FALING. Note, this is me prepping for this lesson. Smile! So, the topic for this lesson is electronegativity. What you need to have the PowerPoint, which is called M&M 3, Matter and Materials 3. It's a PDF. You can download it from the school's website. You need your chemistry textbook. We're working from page 28 to page 34. That's the Doc Scientia book. The homework we're going to be doing would be exercise 3, which is on page 33. It's going to be number 1 to 5. You need your grade 11 definition booklet, and you need a copy of the periodic table, preferably one given out in class so you can see the electronegativity values associated with each element. So if we look at the definition of electronegativity, you do need to look for it in your definition booklet, but here it is as well. The definition of electronegativity is the measure of the tendency of an atom in a molecule to attract the bonding pair of electrons. Please make sure you look at it. So if you look at your periodic table, you will see there's an electronegativity value assigned to each element according to the Pauling scale. Fluorine is the most electronegative. It has a, it has an electronegativity of 4,0. And cesium and francium, right at the bottom of period 1, not period 1, group 1, they have the lowest electronegativity of 0,7. So if you look at electronegativity, it increases upper group and increases across or to the right of a period. The importance of electronegativity comes in the difference of electronegativity. So if we see the Lewis structure of these two molecules, we can see in chlorine, they both have the same electronegativity. So the electrons will be shared exactly in the middle. The difference in electronegativity would be 3 minus 3, which is 0. However, if we look at the hydrogen chloride molecule, chlorine has got a higher electronegativity than hydrogen. Thus, the bonding electrons will be closer to the chlorine than to the hydrogen. Still a shared bond, a shared electrons in a covalent bond, but the distance of the electrons is closer to the chlorine atom and the hydrogen. So this difference is really just simple maths. The sum, as shown on the board, always subtract the smallest electronegativity from the biggest electronegativity, resulting in either a 0 or a positive number. You're never, ever going to get a negative electronegativity. If you get a negative electronegativity, you've done the maths the wrong way around. Redo it. But what does all of this mean? Let's check out this table. Either you can look at the one on the slide or also on page 28 at the bottom of your textbook. The difference in electronegativity helps us predict the type of bond that forms between two atoms. A non-polar bond means the electrons are pretty much shared equally. The difference is 0,4 or less. Note, if the difference is 0, as seen in diatomic molecules, it is also often called a pure covalent bond. There are some gray areas in this section, like 0,4. Is it polar? Is it non-polar? The secret is everything that is not pure is actually very, very slightly polar. Yes, when it's up to 0,4, it is considered non-polar. But at 0,4, rather err on the side of weak polar. A polar bond is when the pair of electrons are unequally shared, resulting in one side being partially negative and one side being partially positive. We talk about this partial positive and partial negative as being sigma positive and sigma negative. The positive side is considered so mostly because there is an absence of electrons, and the negative side because there is a whole gathering of electrons. I wonder what the collective noun for a group of electrons is. Ask your English teacher. Luckily, I'm not your English teacher, hey? The next thing I'm going to say is very, 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 very important. There is a difference between polar bonds and polar molecules. I'm going to say that again. There is a difference between polar bonds and polar molecules. A polar or a non-polar bond has to do with the specific bond formed between the atoms in the molecule, and it has to do with their electronegativity. A polar molecule is a molecule with a pole, a positive pole or sigma positive pole, partially positive pole, and a partially negative pole, aka one side of the molecule is the positive pole and one side of the pole is the negative pole. It is very important to understand that a molecule can have polar bonds but be a non-polar molecule. The shape is extremely important when determining the polarity of a molecule. For example, here, if we look at carbon dioxide and we look at water, carbon dioxide, if we draw the Lewis structure, we know it's a linear molecule because there are no lone pair electrons on the central atom. It has polar bonds because the difference in electronegativity between the carbon and the oxygen would be 3.5 minus 2.5, which is equal to 1.0. Please note that even though there are two oxygens, remember when we're calculating the difference in electronegativity, we're looking at those two atoms within the molecule. So the one C and the one O, or the one C and the other O. We're not looking at the both O's. You're not going to times them by 2 or anything stupid like that. We're just looking at that specific bond, which is the 3.5 minus the 2.5, which is 1.0. However, the molecule has a symmetrical shape. So it is going to be a non-polar molecule. If we look at the water, check there on the top of the water, when we draw the Lewis structure, remember bent or angular. If we look on the top of it, you can see the electrons have gathered up top where the two lone pairs can be seen. That would be the negative pole of a polar molecule. If you look at the bottom where the two hydrogens are, there ain't no electrons around them. So that would be the positive pole of the polar molecule. Hence, water is polar. The bonds are also polar because the difference in electronegativity is 3,5 minus 2,1, which is 1,4. But I know what some of you are thinking. You are thinking, but if I divide the water through the oxygen, I will get symmetry. My answer is nope. Look for possible asymmetry before trying to jump to symmetry. The next two slides very nicely explain to us how we can tell whether something is going to be a polar or a non-polar molecule. So the first and easy thing we must do is the molecule a hydrocarbon? What that means is, does it only have hydrogen and carbon in, like CH4 is a hydrocarbon or C2H6 is a hydrocarbon? If it is a hydrocarbon, it is non-polar. End of story. If it has other things in it, so C and H and let's say O, or C and H and Cl, then it's not a hydrocarbon. Hydrocarbon is specifically just hydrogen and carbon. So if you've now established that it's not a hydrocarbon, you're going to need to draw the Lewis structure. So once you've drawn the Lewis structure, you can determine the shape of the molecule, because you know all the shapes. Remember valence shell electron pair repulsion theory. There's linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and then we also did pyramidal and bent or angular. So based on the Lewis structure, you should be able to determine the shape. Is the shape symmetrical? If it is not symmetrical, the object is polar, or the molecule is polar. So, for example, tetrahedral would be a symmetrical shape. Linear would be a symmetrical shape if there are 3 elements. Something like trigonal pyramidal is not symmetrical. Right, next step. So if it's a symmetrical shape, are the outside atoms all the same? So if we look at carbon tetrachloride, they're chlorine, 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 chlorine. Yes, they're all the same. That would make it non-polar. If the outside atoms are different, say, for example, there were 2 hydrogens there and 2 chlorines, or no, 1 hydrogen and 3 chlorines, then you'd land up with it being polar. The next step that you can do is if a molecule has got hydrogen with fluorine, hydrogen with oxygen, or hydrogen with nitrogen in it, it is always polar. So if you see an HF, whether they're other things or not, if you see an H and an F, or an H and an O, or an H and an N in a molecule, the molecule is going to be polar. Then, if there are lone pair electrons on the central atom, the molecule is always polar. These two slides showing this information with the determining polarity are very important. I'd honestly suggest you print them, stick them in your book, and use them and the process to assist you in working out whether a molecule is polar or not. So what I want us to do now is we're going to do a few examples. So right now I'd like you to pause the video with this sheet up or with this up, and then I want you to make a table in your book, and I want you to draw the Lewis structure, the difference in electronegativity, decide whether the bonds are polar or non-polar, the shape of the molecule, and then whether the molecule is polar and non-polar for the following. For ammonia, for sulfur dioxide, for methane, for HOCl, and for F2, where it is obviously a diatomic molecule. So pause now. Right, I trust you enjoyed doing this little exercise, and here's some answers. So the first one, ammonia. If we look at the difference in electronegativity, it's 3, 0 minus 2, 1, which is 0, 9. Therefore, those are polar bonds. The shape is pyramidal. There's lone pair electrons on the central atom. That makes it a polar molecule. And see, I even gave you a sticker if you got it right. So if you've got stickers or stars at home, you're welcome to give yourself some. Right, the second one is sulfur dioxide. I hope you drew the resonance structure when you drew the Lewis structure, because obviously the double bond could be on the right-hand side or the left-hand side. Sorry, I had to do mine on top of each other like that because I don't have such big, nice space on my little board. Difference in electronegativity, 3, 5 minus 2, 5, which is 1, 0, polar bonds. Shape is bent or angular because there's lone pair electrons on the central atom. So sulfur dioxide is a polar molecule. Methane, CH4. The difference in electronegativity, 2.5 minus 2.1 is 0.4. And remember here I said on the side of polar, so therefore it would be very weak polar bonds. The shape is tetrahedral. The tetrahedral shape is symmetrical. And CH4 is also a hydrocarbon, so therefore it is a non-polar molecule. HOCl. The difference in electronegativity between the hydrogen and the oxygen is 1, 4. The difference in electronegativity between the oxygen and the chlorine is 0, 5. So both of those bonds are polar bonds. The shape is bent because they're lone pair electrons on the central atom, and it's a polar molecule. The other thing we can also note with this one is there's an O and an H. Any molecule that has an H and an O bonded together is going to be a polar molecule. The last one, fluorine, the difference in electronegativity would be 4, 0 minus 4, 0, which is 0. Therefore, it is a non-polar bond. But even better, because it's 0, we could say it is a pure covalent bond. The shape is linear, it is symmetrical, it is a non-polar molecule. Perhaps it's important to note here that all diatomic molecules are going to be non-polar molecules, and all of them are going to have pure covalent bonds. So that was cool. I hope you understood that section. So here's a little subsection of last year's June exam to show how they could ask a question on this section. Please answer these questions and complete exercise 3 on page 33. You can also do activity 3 on page 32 if you want a little bit more practice, but it's not entirely necessary. We will start the next video by going through the answers of these activities. Goodbye, stay healthy, stay home, and God bless.